Is Daodao Yang, who speaks on extreme values of derivatives of the zeta function. Please go ahead.
Yeah, so I start.
Yes.
So I will begin from GCD sums and the spectral norms. And first let's do some warm up so to see what this integral could be. So this two integral. So here this bracket means just the fraction part of it. So it turns out this integral is largely dependent on the GCD and LCM of these two integers. So if you see in this example, you just slightly change by one number, but this answer change a lot. So for generally positive integer m and n, you have this formula. This was first stated by Fresnel and proved by Landau. And why this formula is interesting? So originally this is coming from a problem Hardell Littlewood. They try to study how large this integral could be in some approximation theory. So if you're expanding the square and use the result in previous slides, then this leads you to study this GCD sum. And Orders, he proved that this sum is bounded by n log n. And the correct size was found by Gale, who said this should be n log n squared. So this two different constant. But he didn't find the sharp constant in his theorem. The sharp constant was found by Levico-Radziwiłł in 2014. So they found it's E2 gamma over zeta 2. So this is their result. So generally, you can consider GCD sums like this. So when you give a sigma positive, be fixed, you can consider and give a set m of positive integers. You can consider this sum. Again, this bracket means GCD of m and n, and this just means the LCM of m and n. So this is a general definition for GCD sum. Let's see an example first. Just to see this simple example. So suppose the set is 1, 2, 3, 6. Let's compute its GCD sum. So if m equal to n, so GCD of mn is 1, and so in this case, GCD of mn is equal to LCM of mn, so it's 1. So this give 1 here, and you have 4 such pairs. And let's say what kind of case is this summand can equal to 1 over 2 sigma. This can only have 4 pairs, namely when mn equal to 1, 2, or mn equal to 3, 6. And we get also 4 multiple here. And similar, you can get 2 other summands also with 4 as a multiple. So you can write this as a product. So this simple construction can be generalized to a more general situation. So if you let M to be the set of all square-free integers composed of the first R primes, then the cardinality of the set n equal to 2 to the power R. And by the argument before, you can get this result, this GCD result. And by prime number theorem, you can get this lower bound for this GCD sum. Actually, this simple construction is almost optimal for sigma between half and 1. So this is a theorem by Eisenstein, Bakers, and Sieg. They say if sigma is between half and 1, you have this result. this is almost optimal up to some constant, different constant here. So next, I want to talk about spectral norms. The spectral norms of GCD matrix is defined as this. Here, C is some complex vector with length 1. So this spectral norms is larger than the normalized GCD sums. To see this, you can take this Cm equal to 1 over square root n if and only if m is inside the set M, otherwise you just put it 0. Then you will find that this spectral norms is larger than this normalized GCD sums. And I want to mention the spectral norms result of Leverkusen residue. They prove that on one line, you have this result. And by the inequality mentioned in previous slides, you can immediately get the sharp upper bound for this GCD sums. Next, I want to talk about extreme values of the Riemann zeta function, the methods. I will mention how the GCD sums can be used to get large value of zeta. So first, I want to mention some older result of Born-Landau, who proves such a result on one line. Later, their result was refined by Littlewood, said give explicit what the constant should be. Littlewood constant was again improved by Leviation, and this result are further improved. So before state new results, let's talk about some notation. So here, this log j will be the j's iterated logarithm, this notation. So for instance, log 2t is just log t, log 3t is log t. So this is a further improvement by Granville and Sand. So they have some new factor plus log 3t, but they need to minus log 4t. And the result of Isana, Manhattan, and Munch, they can move the result of minus log 4t, and this is the best known result so far. And next, I want to mention that on the other hand, when you assume the Riemann hypothesis, Littlewood says the upper bound is bounding by different constant, but the size is correct. And this is a recent result by Lanzuri, Xianan Li, and Sand. They have improvement of Littlewood's result. And also in the critical strip between half and 1, you have such omega result. And on the half line, Montgomery, he gets this result when assume Riemann hypothesis is true. Next, I want to mention the result by Sand. So he further improves the result of Montgomery, also earlier result of Balasambra and Ramachandra, and his result is unconditional. So now I also want to mention that on the other hand, when you assume Riemann hypothesis, you have this bound due to Littlewood. And this was improved by Chandy and Sand only by constant. So they proved that any constant larger than log 2 over 2 can, in this theorem, is fine. And then I want to talk about the methods to obtain the large values. So first, talk about Voronih's method. So he defined the two integrals like this. Then the maximum value of theta will larger than the square root of the ratios. And he chose this phi t like some Euler product and compute it, and he gets this result. But note, this result is weaker than Montgomery's bound. Next, I want to talk about Sand, his resonance method. He consider more general Dirichlet polynomial. And he defined two integral m1, m2 like this. Then the maximum value is larger than the ratio. And moreover, he computed m2, m1 like this. So when you take a ratio, you will find the problem that you need to understand how large this could be. And he solves the optimal problem to be this expression. As a corollary, he just take n equal to t to the power 1 minus epsilon, and he can get this result. And next, I want to mention Hilberding's work. He do some interesting results, use Sun's method. He replaced zeta plus it squared by this zeta plus it squared. But again, his result is weaker than previous result of Montgomery. Now I want to talk about Eisleiner's work. So Eisleiner, he used some long resonators. So in his resonator, he do not have the restriction that the integer n should be smaller than t to the power 1 minus epsilon, say. So this integer can be arbitrarily large. And he also defined the two integrals. And he found if you define this resonator in some way, then the maximum value take square is larger than this GCD sums. And remember this result I mentioned in previous slides. So from this GCD sums, he gets this lower bound. This matches the lower bound result of Montgomery, but these constants are slightly improved of previous result. So next result is due to Bonduricon shape. So on the half line, so they solve this optimal problem up to some constant, and they found the GCD sum should be like this. So they have some extra factor here, and as a result, they get this huge improvement compared to previous result of sound. So they have an extra factor log 3t here. And they also have some slight improvement after 2 years of the result. And to find the optimal constant, this is done by De La Petite and Tenenbaum. And as a result, they improve the constant of Bonduricon shape. So this is their result. So now I want to talk about extreme values of derivatives of the Riemann zeta function. So inside the critical strip, so the only literature I can find about extreme values of derivative zeta function is due to Kelmerling. So he considered some region near the one line, like this, in his definition, and he proved such omega results. And but he didn't establish the vertical lines omega result. So this was done by me. So I proved these two results inside the critical strip. So the lower bound match with the lower bound of zeta. So this is the result. And the ideas of the proofs is a derivative of zeta. You have this expansion, and this log NL is almost larger than 1. So you have some similar argument to tell you the maximal square is larger than the GCD sums. So you can use previous result on GCD sums to get large values of the derivatives. However, on the one line, the contribution of this log NL will be large. So we will need some more delicate estimate. So use Sun's resident methods, I define two integral m1, m2 like this. So the maximum of the derivative is larger than the ratio, and it's turned out to be larger than this. So the key object will be this ratio. So we try to understand how large could it be. So my result on last year is this one. And as a result, I get this. So anyway, so this is log 2t size and the power is L+1. So compared to the result of boron and Landau is log 2t. And so it's a kind of generalization, but the constant here is too small. So there's some improvement by Zikandong and Bingwei. So they refine my argument and slightly improve this constant. However, we still have the limit of this constant goes to 0 when L goes to infinity. So here I have some further improvement, which I done recently. So this constant was improved to some YL, which is this integral. Here, rho u means Diekmann function. So the important is first, this is larger than the constant of Dong and Wei. And also log of this constant is asymptotically L log L when L goes to infinity. So in particular, when L goes to the infinity, this goes to infinity, which significantly improves previous results. This can also be established by for Dirichlet L function. This is a result. And I want to talk about some computations. So maybe some people doing combinatorial may be interested. So if you let BL be the L's complete exponential Bell polynomial, then the constant YL can equal to this expression. For instance, you have these first three examples, these three Bell polynomials. From here, we can compute y1 equal to E gamma, y2 equal to 3 gamma over 2, and y3 is the 70 E gamma over 6. As a result, we get these examples. Next, I want to talk about the ideas of proof. So first, let's record how people can prove a result for zeta, forget about derivatives. So first, though, people have some conjecture that this on one line that it have approximation by this short Euler product. And here we have this Merton's formula. And use resonance method and Merton's formula, we can get this result here. And note that this we can write this Euler product in another form. So we can write as this infinite sum. Here, P plus K means the largest prime factor of K. And the conjecture on zeta, inspired the conjecture on derivative should be look like this. So it can also be proven by some infinite theorem, but support on smooth integer. And and also we have this nature conjecture compared to the zeta case. So now I want to talk about how to compute this. So first we have this psi function. This is counting integers smaller than x and with prime factors at most y. So Diekmann found a function now called Diekmann function, which is defined for one between when the variable between 0 and 1 and satisfy this differential equation. And he found this counting function have this kind of formula. And we use partial summation properties of Diekmann function. We can get this result. So this suggests us the answer to the optimum problem. So here, this is a lower bound I prove. So from this result, I get the improvement the theorem stated before. So next, I want to talk about some conditional upper bounds and the symptomatic formula for large value of the zeta and the L function. So first, assume RH and GRH, we can get, this is almost the same size as before, but here the constants are slightly different. In both cases, we have some extra factor 2 to the power L plus 1. So this is like a Littlewood result for the upper bound. The Littlewood also have an extra factor 2. So when you take a derivative, you have this also extra factor. So the important ingredient is the work of Granville and Sand on character sums. So when assume GRH, they assume the character sum can be smooth, can be approximated by character sum over smooth integers. So I prove some similar results. I see the exponential sum can also be approximated by exponential sum over smooth integers. So this gets the previous result. Next, I want to mention the Granville and Sand conjecture. So this is a conjecture about also in the same type, approximates these correct sums by correct sum over smooth integers. But here they can take y to be log Q smooth, more precisely, this is log Q smooth. So from this result, we can get a asymptotic formula. So here is the result. So assume this conjecture is true, I can get this upper bound. So in particular, when I assume the Granville-Sand conjecture is true, and when Q is prime, when it goes to infinity, I can establish such asymptotic formula. And I also have a similar conjecture for the exponential sum, like the case for character sums. And assume my conjecture is true, I also establish this asymptotic formula for the case of zeta derivatives. Next, I will mention log-type GCD sums. So in the resonant method, if you consider two integral like this, so here you consider zeta square, derivative square, and then you will get this lower bound, and if you expand what this is, and you will discover the log-type GCD sums. So this log-type GCD sum is almost the same as GCD sum, but it's more complicated because it have two extra log factors like this. And when sigma between half and 1, this is basically GCD sums, not so many difference because this log NL factor have small influence. But on the one line, the GCD sum, log-type GCD sum, can be interesting. Moreover, the log-type GCD sums, if you know it can be large for some sequence, then you know the derivative zeta can also be large along some sequence. So I also give you the character size. So this suggests us the log-type GCD sum should be the character sum should be log NO to the power 2 plus 2L. In fact, this is true. I prove this. And this can be viewed as a generalization of Gell's theorem. His theorem states the result when L equal to 0. So I talk about the method to prove this. So for the lower bound, I first split the GCD sum into two parts. For one part, it's larger than some so this is a result by Loveco residue. And I split two parts. One part is more than 2 delta times this sum. Another time is less than 1 minus 2 delta times this sum. So also inside the first sum, this log factor can be large. So as a corollary, I get this character bound, character order bound. And to consider the upper bound for this log-type GCD sum. So from the conditional result of zeta, we know this should be true. But how to prove it? So if we take the derivatives for GCD sum, we can get this extra log factor. Actually, this one is larger than this log-type GCD sum. So this suggests us to think about the problem like this. So if you, by this simple inequality, you know this sum is smaller than this sum. In particular, if epsilon goes to 0 sufficiently fast, then you can get a nice band for this GCD sum, which can give you a nice band for this sum with logarithm factor. Indeed, this is true. So I prove this result. So if this alpha can goes to 1 sufficiently fast, then the spectral norm also the same size as the spectrum on the one line, but with some different constant. As a corollary, I guess this sum is smaller than this log n 2 plus 2l. Remember, this is larger than GCD, log type GCD sum. So I get log type GCD sum, upper bound. And the method to prove this is using the random zeta function. So it's defined as a random, it's a product of over random factor. And the method of Lovico and residue shows that the spectral norm can be bounded by such expression. So the problem now becomes to understand the expectation for this quantity. And they have this result for critical strip, and they use the result on one line to prove their sharp upper bound. And in order to prove my result, we also only need to prove such a result when alpha is sufficient close to 1. And this, because we have the result on one line, so we only need to prove such a result, which needs some work. I will not mention here. And this is end of my talk. Thank you.